lectures on control systems laboratory. In this video, we will discuss the digital simulation of step response of type 0 unity feedback second order systems. That means we are taking a second order type 0 system. For that, we are giving step signal as the input, and we need to find the output response through simulation. Coming to the aim, obtain the step response of a unity feedback system type 0 second order system with an open loop transfer function g of s equal to 100 by s square plus 10.18 s plus 100 by MATLAB simulation. If you observe the open loop transfer function 100 by s square plus 10.18 plus 100. So here the highest power of the denominator is s square. So it is a second order system and we are not having any polar origin. So it is a type 0 second order system. For this second order system, we are giving a unity feedback and then we need to find the closed loop transfer function. Once if we know the closed loop transfer function, then you need to analyze the time domain specification, that is the transient response, and also need to cross check the steady state response. That means we are finding the transient response means we are finding the rise time, peak overshoot, settling time, and coming to the steady state. Coming to the steady state, we need to identify the steady state output. That means first we will identify the steady state error. From if you know the error, from that you can identify the steady state output. The same way for the three cases. That means here we are taking three systems, three open loop systems. For the three open loop systems, we are giving a unity feedback, and then we are applying a step response, step signal as a input, and we will find the output response. And coming to the second case, we are taking open loop transfer function g of s equal to 100 by s square plus 28.28 s plus 100 is the open loop transfer function for the second case. The same way coming to the third case, the open loop transfer function is 100 by s square plus 100s plus 100. If we observe all the three transfer functions, the highest power is 2 in the denominator term. So it is a second order systems, and we are not having any polar origin. All the three cases, we are not having any polar origin. That means it is a type 0 system. So type 0 unity feedback second order systems. For these three systems, we will apply a step input and we will analyze the output response both in transient and also in steady state. In transient means we are observing rise time, peak overshoots, settling time, and coming to the steady state, we will observe the steady state output. And finally, after getting all these values, we will compare the damping ratio. Depending upon the damping, what about the changes and all is there, how we can get the better damping system. Based on that, how we can design a proper control system. Okay, study the effects of damping on the system response by comparing the above three responses and comment on the significance of damping. What is the necessity of damping? Which one is the best one? Okay. So is in simulation experiment. First, we need to do the calculation part. There is a theoretical calculation. So first, we are taking reference as a first system. So first open loop system. Right. So first open loop system is 100 by s square plus 10.18 s plus 100 is the open loop system, and it is an unity feedback. So from this we need to identify the closed loop transfer function. So the closed loop transfer function is c of s by r of s is equal to c of s by r of s is equal to g of s by 1 plus g of s into h of s. G of s by 1 plus g of s into h of s, right? So we know the g of s open loop transfer function and a unity feedback, that means h of s is 1. If we substitute all these values, then we are getting the closed loop transfer function as a 100 by s square plus 10.18 s plus 200. This is the closed loop transfer function. This is the closed loop transfer function for the first case. Closed loop transfer function for the first case. That is 100 by s square plus 10.18 s plus 200. Now we are comparing this closed loop transfer function with the standard form of the second order system. Standard form of the second order system. That means c of s by r of s equal to omega n square by s square plus 2 zeta omega ns plus omega n square. Now we will compare this denominator term with our closed loop transfer function. From that omega n square is equal to 200. From that omega n we are getting as a 14.14 radians per second. Once if we know the omega n, then 2 zeta omega n, which is equal to 10.18. Now already we know the omega n. If we simplify and if you get the zeta as a 0.36 for the first case. For the first case, the closed loop transfer function is this one. And from this, if you find the zeta value you are getting as a 0.36 and the omega n we are getting as a 14.14 radians per second. Now by observing this damping ratio directly, it is in 0.36 means it is an under-damped system. Zeta value is in between 0 and 1. So it is a under-damped system. And coming to the nature of the output response, here we are having exponentially decreasing sinusoidal oscillations. Zeta value is under-damped means the output will be the exponentially decreasing sinusoidal oscillations. Okay, once if you know the zeta and omega n, then you can identify the time domain specifications. That means you can analyze the transient response. So rise time, peak time, settling time, maximum peak, overshoot. What is the formula for rise time? That is Tr is equal to pi minus tan inverse of root of 1 minus zeta square by zeta by omega n into root of 1 minus zeta square. Now already we know the zeta value, we already know the omega n value. If we substitute, and we are getting as a 0.0995 seconds is the rise time. And coming to the settling time, Ts equal to 4 by zeta omega n. Already it's a zeta and omega n value. If we substitute, we are getting the settling time as a 0.7693. And coming to the overshoot, maximum peak overshoot, e power minus pi zeta by root of 1 minus zeta square into 100. So if we substitute zeta value, then we are getting overshoot as a 29.73%. And in the same way, peak amplitude and also peak time we are finding. This is the for program one. That is the first case. In the same way, we need to check for the second case also. That means in the second case, the open loop transfer function is 100 by s square plus 28.28 s plus 100. Now, here feedback is 1. So once if we know the g of s and h of s, we need to identify the closed loop transfer function. That is g of s by 1 plus g of s into h of s. So here also we are getting as a 100 by s square plus 28.28 s plus 200. That is the closed loop transfer function. And from that closed loop transfer function, we need to identify the zeta and omega n. Once if we know the zeta and omega n, then we can calculate the transient response parameters. That is rise time, settling time, overshoot, peak amplitude, and peak time. Coming to the second case we are getting zeta as a 1. That means it is a critically damped system. Second case at zeta we are getting as a 1. That is a critically damped system. Right. Similarly for third case also. That is the third case open loop transfer function is 100 by s square plus 100s plus 100 is the open loop transfer function. And now if you convert into the closed loop means here we will get as a 100 by s square plus 100s plus 200 is the closed loop transfer function. Compare with the standard form. And then here we are getting as a overdamped system. Zeta value is greater than 1 will come. So it is an overdamped system. For that overdamped system also, we need to find the rise time, settling times, overshoot, peak overshoot, and peak times. If we observe the second and third cases, it is an critically damped and overdamped systems. In the critically damped and overdamped, we are not having any oscillations. So overshoot will be 0. This is the transient analysis part. And coming to the steady state part is the open loop transfer function. Now we are applying a step input. If we apply the step input, the error constant will be the positional error constant Kp. For all the three cases, we are applying a step signal as an input. So here we are getting a positional error constant. Once if you know the positional error constant, from that we can identify the steady state error. Okay. Coming to the first case, the open loop transfer function is 100 by s square plus 10.18 s plus 100. So by using this one, we are finding the positional error constant Kp equal to limit s tends to 0. G of s into h of s. Here this is the open loop transfer function we are taking as a g of s, and the feedback element is 1. If we substitute this one and apply the limits s tends to 0. If s tends to 0 means we are getting 100 by 100. That means 1. Kp value is 1. If we substitute the Kp value as a 1, that is 1 by 1 plus Kp. That means Kp is 1. If we substitute, then we are getting steady state error as a 0.5. We are applying a step signal as an input. That means magnitude is equal to 1. And here we are having a steady state error is 0.5. So finally, we are getting the output as a final value will be 0.5 only. The same way coming to the second case is the open loop transfer function g of s 100 by s square plus 28.28 s plus 100. So from this, we are applying a step input. So we need to find the positional error constant. So the positional error constant Kp is limit s tends to 0, g of s into h of s. H of s is 1 unity feedback, and if we substitute g of s and apply the limits s tends to 0, then this denominator term, these two terms will be 0, 100 by 100, we are getting 1. So again, the steady state error will be 0.5. If the steady state error is 0.5 means the final output value C of t we are getting as a 0.5. The same way coming to the third case. Coming to the third case, the open loop transfer function is 100 by s square plus 100s plus 100. So if we substitute and apply the limits, we substitute the g of s and h of s and apply the limits, that is s tends to 0, then this denominator term, this 2 will be 0, again 100 by 100, we are getting Kp as a 1. So from this, we are getting the steady state error as a 0.5. The steady state error is 0.5. The steady state error is 0.5, then we are getting the output response C of t as a 0.5 only. Right? For all the three cases, we are having a steady state error is 0.5, and the final value will be C of t final value will be 0.5 only. Right? This is the theoretical calculation part. Once the theoretical calculation is over, now we need to write the coding part. We will write the program for all the three cases and we will simulate in MATLAB. Yeah, coming to the apparatus required, we need a personal computer and a MATLAB software. And coming to the block diagram, that means here open loop system is the G of S is the open loop system. For that, we are giving a unity feedback. For that, we are giving unity feedback, and then we are applying a unit step signal, and we are finding the output response. From this output response, we are analyzing the transient and also the steady state. Okay, coming to the first case. Coming to the first case, this is the open loop transfer function. If you are adding a feedback, unity feedback, then you are getting the closed loop transfer function will be like this. 100 by s square plus 10.18 s plus 200. So while writing the program also, first we need to specify the open loop transfer function, and then we are adding a feedback, and the total combination already existing system and the feedback element total combination will give the closed loop transfer function. For that closed loop transfer function, we are applying a step input and we will analyze the system response. Okay, the first one will be the open loop transfer function. That means here we are having a numerator and denominator, so we need to enter the numerator coefficients and then denominator coefficients. Coming to the numerator coefficient, we are having 100. 100 is the numerator coefficient. So first we are entering the numerator as a 100. And coming to the denominator coefficients, s square coefficient is 1. S square coefficient is 1. And the next highest power is s power 1. So s power 1 coefficient. S power 1 coefficient is 10.18. S power 1 coefficient is 10.18. And next s power 0 coefficient is 100. So 100 is the denominator coefficients. Once if we know the numerator and denominator, then we can frame the open loop transfer function. We are assuming open loop transfer function name, we are assuming as a SYS system. SYS equal to TF. TF is a predefined function, transfer function. So TF of numerator comma denominator. So this the open loop transfer function is there. And now we need to give the unity feedback. So that one unity feedback we are assuming as a variable h equal to unity means 1. So this is the unity feedback element. Now the combination of already existing system and this feedback element will give the new system, that is the closed loop transfer function. We are assuming as a SYS1. Closed loop transfer function we are assuming as a SYS1, which is equal to feedback of already existing system, comma feedback element h. Unity feedback element h will give the closed loop transfer function, closed loop system. Now for that closed loop system, we are applying a step input. For this closed loop system, we are applying a step input. Step of SYS1 will give the final output. Waveform will come. From that waveform, we can observe the all time domain specifications and also the steady state value. That is the final value also we can check. This is the coding part for the first program, first case. And the same way coming to the second case. This is the open loop transfer function. If we convert into the closed loop, this is the value we are getting. That is SYS1 equal to 100 by s square plus 28.28 s plus 200. This is the closed loop transfer function. So here also first we will specify the open loop system parameters, and then we are adding the feedback element, and the total combination will give the closed loop system. For that system, we'll apply the step input. That means coming to the open loop system, numerator coefficient 100, and coming to the denominator coefficient, highest power is s square. So s square coefficient is 1. S square coefficient is 1. And next highest power is s power 1. So s power 1 coefficient is 28.28. And S power 0 coefficient is 100. So once if we know the numerator and denominator, by using these two, we are framing a transfer function, open loop system, SYS equal to df of numerator comma denominator, df of numerator comma denominator. And next we need to give the feedback element. We are assuming as a h equal to 1, a combination of already existing system and the feedback element will give the closed loop system. For the closed loop system, we are applying a step input. Right. In the same way, coming to the third case, here is the open loop system and this is the closed loop system. First, we need to give the open loop system data. That is a numerator and denominator coefficients we are representing. By using these two, we are framing a closed loop. We are framing a open loop transfer function. Once if we know the numerator and denominator, by using that we can frame the transfer function. That is the open loop system. Now we are adding a feedback element. So the combination of existing system and the feedback element will give the closed loop system. For the closed loop system, we are applying a step input. For this closed loop system, we are applying a step input. Right, this is the coding part. Now we'll open the MATLAB and we can enter this coding part and we will see how the response will come, how to find the rise time, delay time, all steady state parameters also. Okay, now we'll open the MATLAB. Yeah, it's already open. So now we need to enter the program. So we'll enter the program, the script file. You can enter in command window also, but here it's not possible to save. We can view the result, but it's not possible to save the program. So for that, we are opening a new script file. So in editor box here, we can enter the program. So for the programming, coming to the programming part, the first line will be always CLC. That means first it will clear the command window. Previous data, anything is there, that it will clear everything in the command window and it will run the current program and it will show the current data output only, current program output only. We will enter the first program. So there is a first case. So coming to the first program, numerator coefficient is 100. And next coming to the denominator coefficients are square bracket 1 space 10.18 space 100. This is the denominator coefficient. And once if you know the numerator and denominator, we are framing a open loop transfer function, that is SYS equal to predefined function TF transfer function of numerator comma denominator, right? And then we are giving a unity feedback element. We are assuming as a h, variable h, anything we can take. H is equal to 1. And now the combination of already existing system and this feedback element will give a new transfer function that we are assuming as a SYS1 equal to feedback of already existing system is SYS, comma feedback element is H. So now we are getting the feedback, that is the closed loop transfer function for that system. Now we need to apply the step input. So step of closed loop system name is SYS1. Right. Now we'll save the program and we will run. So first we'll save the program. Yeah, we are saving with a design step response. So step response 1, first program step response 1. Right, we save the file. Need to save properly. After saving the file, we'll run the program. Somewhere it is showing error. We will copy the data and we will open the new script and here we will enter. Yeah, now we'll check. Yeah, here also need to save the file. Let it be untitled only. Okay. Yeah, now it is running. We check output also coming. So okay. First we will see what is the command window we are having, what all data is there. Later we can check the waveform. So coming to the command window, first we enter the numerator details. So that is 100. Next coming to the denominator details, we entered 1, 8, 10.18, 100 is the denominator. By using this numerator and denominator, it is framing an open loop transfer function. That is 100 by s square plus 10.18 s plus 10.18 plus 100 is the open loop transfer function. And then we are giving a unity feedback, h is equal to 1. We are giving a unity feedback and the combination of already existing system and the feedback element will give the closed loop transfer function, that is SYS1, which is equal to 100 by s square plus 10.18s plus 200. This is the closed loop transfer function. Now for this closed loop transfer function, we applied the step input. So we are getting the graph. So from graph, we will observe all the details. So and one more thing here, already we know the zeta value. What is the zeta value for this one? It is in 0.36. That is, it is a underdamped system. Underdamped system is exponentially decreasing sinusoidal oscillations. That's why the waveform also, if you observe, we are getting the maximum peak, and again it is decreasing steadily oscillations, exponentially decreasing sinusoidal oscillations, right? And now we'll identify what is the rise time, what is the delay time, peak time, everything you can check. First, coming to the characteristics, and we'll check the peak response. That means peak data. System name SYS1 closed loop system. What is the peak amplitude? Here we are having 0.649. Peak amplitude is 0.649. Already theoretically we did the same thing only. Okay, right? And coming to the overshoot, maximum peak overshoot 29.7. And the peak time is 0.235. Peak time is 0.235. Right? And we'll see the next settling time. We'll see the settling time. Settling time for the first system. Settling time for the first system is 0.769. Time taken to enter into the settling time. Steady state is 0.769. And we'll see next rise time. We'll see the rise time. Yeah, rise time is 0.0995 seconds. Already same value we will get during theoretical calculations also. And now finally we will check the steady state data. Yeah, here it is still. Yeah, we check the final value, how much we are getting, 0.5. Here we are having a steady state error is 0.5. If we are removing that, then we are getting the final value as a 0.5. This is the result for the first case, first program. Okay, in the same way, next we need to check for the second program, that is the second case, and also for the third case. We'll close the graph. Now we will enter the second program data. This is the second program data. In second program data, directly we'll copy and paste there, and we'll see second program. And the same thing we are copying in MATLAB. Yeah, right. This is the second program. Now we'll run. Yeah, graph came. First we will check the command window. Later we will see the graph. Yeah, coming to the numerator 100 and coming to the denominator 128.28 100. So once if we know the numerator and denominator, we are framing the open loop transfer function 100 by s square plus 28.28 s plus 100, and we are giving a unity feedback. The combination of this unity feedback and the existing system, unity feedback and the existing system will give the closed loop transfer function. That is, the closed loop transfer function is 100 by s square plus 28.28 s plus 200. This is the closed loop transfer function. For this closed loop transfer function, we applied a step input and we need to analyze the output response. Already we checked this one. This is a critically damped system. Critically damped system means we are not having any oscillations. We are not having any oscillations, exponential term only. This is the output response for the second system. Here we need to cross check all the parameters. Go to characteristics. In characteristics, peak response. Where we're having the peak response, here it is there. Peak amplitude is 0.5, overshoot 0. Here we are not having any oscillations, means overshoot will be 0. And coming to the peak time is greater than 0.8 seconds it is showing, right? And coming to the remaining parameters, settling time. So here it is the settling time. Settling time is 0.412 seconds. Settling time is 0.412 seconds. The same way, rise time. Rise time is 0.237. Rise time is 0.237, right? And next we will see the steady state value. We'll see the steady state value. Yeah, steady state value, the final value. Final value is 0.5. We are getting the steady state error as a 0.5, and the remaining will be the output. That is the final value. What we are getting is 0.5. This is the second program, second case. In the same way, now we need to check for the third case also. We'll open the third program. We'll copy the data. And paste it in the MATLAB script file. Yeah, we enter the new, that is the last case. Now we'll run the program graph game and we'll see command window first. Yeah, numerator we gave as 100 and coming to the denominator 100. So the open loop transfer function will be 100 by s square plus 100s plus 100 is the open loop transfer function. And then we are giving a unity feedback element h is equal to 1. So once if you know the open loop and feedback element, then we are finding the closed loop transfer function, that is 100 by s square plus 100s plus 200. This is the closed loop transfer function. Once if we know the closed loop transfer function, for this we are applying a step signal as an input, and now we need to analyze the output and response. So already graph came. We'll check the graph. Yeah. And one more thing, here we already know that this is an overdamped system. Overdamped means here also oscillations won't be there. Okay. And now we'll check the output responses, characteristics, peak response. Yeah. Peak response. System name, peak amplitude is 0.499. Overshoot, we are not having any oscillation, so overshoot will be 0. And peak time is greater than 3 seconds. Peak time is greater than 3 seconds. Okay. Now we will see the remaining data. Go to characteristics, settling time. What is the settling time for the third case is 1.93 seconds. Settling time for the third case is 1.93 seconds. Next, we'll see the rise time. So rise time is 1.08 seconds. Rise time is 1.08 seconds. And next, we'll see steady state. We'll see the final value. What is the final output? Final output will be 0.5. That means here also, third case also, we are having a steady state error is 0.5. So the final value will be 0.5. Like this, you can identify all the time domain specifications, that is both transient and steady state parameters. Right. And coming to the programming for ordinal waveforms, we are getting, yeah, after entering the program, we are getting the values, that is the output. Output will be like this, the program response, first program response. For the first program, we are checking the rise time, peak amplitude, overshoot, settling time, final value. And this is the second program response. And this is the third program response. Right, we checked all the transient and also the steady state parameters. And now coming to the conclusion. So first, damping ratio and undamped natural frequency of type 0 second order system. This is the first case. For the first case, how much you are getting? 0.36 and 14.4. 0.36 means it is an underdamped system. For the underdamped system, what is the rise time you are getting? What is the peak time you are getting? What is the peak overshoot? What is the settling time? And what about the steady state error? So based on this damping ratio, directly we are saying it is an underdamped system. So for the system, these are the ranges values. What you are getting, rise time is 0.101 second, peak time is 0.229 seconds, peak overshoot is 29.5 seconds, settling time is 0.769 seconds, and the steady state output is 0.5. This is for the first case. And coming to the second case, the zeta value is 1 and the omega n value is 14.4 radians per second. Zeta value is 1. Zeta value is 1 means it is a critically damped system. Critically damped systems, here we are not having any oscillations. It is a non-oscillatory. It is a critically damped system. For this critically damped system also, we find the rise time, settling time, steady state output. Right, this is the third case, second case. And coming to the third case. In the third case, whatever the damping ratio we are getting, 3.54 and 14.14 radians per second. 3.54 and 14.14 radians per second. So here it is an overdamped system. Here also we are not having any oscillations. It is an overdamped system. For the system also we find rise time, settling time, and the steady state output. And if we compare all these three systems, then you can observe the damping ratio. What about if we are increasing the damping ratio? If we are increasing the damping ratio means rise time is increasing. If we are increasing the damping ratio means rise time is increasing. The rise time is increasing means the system response becomes slower. Slowly it is responding. Slow in response, right? If we are increasing the damping ratio means the rise time is increasing. Rise time is increasing, system becomes slower, right? But coming to the all the three cases, the steady state error is 0.5 and the final value of the output is also 0.5, even though the output is same, but it is taking more time. It's taking more time, however, increasing the damping ratio. And also, if you observe one more thing, it reduces the overshoot. Reduces the overshoot. So while selecting the damping ratio, we need to cross check rise time and overshoot. Based on that, we can design the system. We need to check, we need to select a proper value to satisfy all the parameters. Okay, thank you.